intelligent analysis method of multidimensional time series data based on deep learning. Chen Zhongwei, College of Information Engineering, Guangxi University of Foreign Languages. Abstract. In order to improve the intelligent analysis performance of multidimensional time series data, an intelligent analysis method of multidimensional time series data based on deep learning is proposed. The deep learning network model is used to establish the distribution function of correctly classified and wrongly classified data. According to the calculation process of the deep learning network, the outliers of multidimensional time series data are mined. The feature space of multidimensional time series data is determined using the k-nearest neighbor method. The multidimensional time series data is reduced in dimension by calculating the covariance matrix of multidimensional time series data, and the time series data is classified according to the preference level. Abstract. The characteristics of multidimensional time series data and combined with the design of multidimensional time series data analysis algorithm to achieve intelligent analysis of multidimensional time series data. The experimental results shows that the method in this paper can reduce the mean absolute error and root mean square error to within 0 to 0.25 to 0.3 respectively in the intelligent analysis of multidimensional time series data, and improve the analysis performance of multidimensional time series data. 1. Introduction. Time series data features to time series data, which is a data column recorded by the same indicator in time sequence. The analysis of time series data mainly predicts annual time series data by analyzing the existing time series data and constructing a time series model. The difficulty of time series data analysis lies in how to grasp the characteristics of historical time series data and more effectively predict future time series data. Within the extensive application of IoT technology in smart cities, Industry 4.0, supply chains and home automation, it has generated massive data according to a research report of Cisco. By 2021, the number of devices connected to the Internet of Things will reach 12 billion, which means that the data traffic generated each month will exceed 49 exabytes, whether in the industrial field or in the life field. The use of sensors is everywhere. A large amount of data and information generated by these sensors has gradually become the most common data form in the application of the Internet of Things. Therefore, in the application of the Internet of Things, the analysis and processing of this data has become increasingly important. The whole IoT architecture consists of data perception layer, data transmission layer, data processing and storage layer, joint learning and analysis of IoT application layer. Through the analysis and processing of the data collected by these sensors, more valuable and meaningful information can be obtained, thus providing guarantee for more intelligent decision-making, deployment, and supervision of these IoT applications. 2.1 Mining multi-dimensional time series data outliers. Due to the small scale and wide range of time series data, it is very easy to regard abnormal values as wrong or invalid data during analysis, which will also affect the overall accuracy of multidimensional time series data, cause misunderstanding, and increase the difficulty of analysis. Therefore, we use deep learning network technology to mine outliers of time series data. The deep learning network model is shown in Figure 1. From the above figure, it can be found that the composition of deep learning network model mainly includes the input layer, the hidden layer, and the output layer corresponding to the input value weight, and output function. The basic relationship between the different components is shown in the following formula. 2.2 Dimensionality reduction processing multidimensional time series data. First, the k-nearest neighbor method is used to determine the domain of sampling points in the z-dimensional time series, and then the nearest neighbor graph G is constructed. The nodes in Figure G correspond to the points in, and the edge in Figure G represents the nearest figure relationship between points. Calculate the approximate geodesic distance. Select two nodes, xi and xj in Figure G, and measure the approximate geodesic distance of the shortest path between them to obtain the matrix. The process of constructing the nuclear matrix is shown in formula. In the formula, so as to ensure that the matrix is positive semi-definite, after calculating the R eigenvalues of H, the eigenvalue matrix can be obtained, and the corresponding eigenvector. Finally, the embedded coordinates of the m sample data points in the R-dimensional space can be obtained as follows. 2.3 Extracting multi-dimensional time series data features. The multi-objective decision-making theory in operational research is a challenging and active branch field. Based on the decision-making background, multi-objective decision-making considers several evaluation indicators that may conflict and diverge with each other, and combines optimization theory, statistics theory, management philosophy, and operational research methods to optimize and rank multiple alternatives. The proposed method abstracts the characteristics of time series data on the basis of multi-objective decision theory, and the specific steps are as follows. The standard decision matrix C is constructed according to the extracted interval extreme point sequence. The rows and columns in the decision matrix C are the extreme points existing in the time series data, and the object attributes corresponding to the extreme points. That is, the multi-objective Criterion. Let the vector A be a set composed of m disjoint points, and the vector B be a set composed of m disjoint point attributes, which is the evaluation index. After standardizing the decision matrix, the decision objects corresponding to different indicators are compared by the following formula. 2.4. Designing multidimensional time series data analysis algorithms. On the basis of completing the feature exception of multidimensional time series data, grid is introduced as index calculation to grid the activity space of multidimensional time series data in the network. That is, the division method of longitude and latitude is used to discretize the activity space of network multidimensional time series data into four several grids of size. After the grid division is completed, the active position points of the network multidimensional time series data are mapped to the corresponding cells one by one. After the grid division, the length reference value and width reference value of each cell can be calculated by the following formula. 3.1. Experimental environment and settings. The experiment was run on Windows 10 operating system with AMD Ryzen's CPU, 16 GB memory, and Force RTX 2060 graphics card. The deep learning platform Keras 2.0.8 is used for network model building and training, and the TensorFlow GPU 1.4 is called to complete the accelerated operation. The parameter settings of each layer of by predictor are shown in Table 1, where filters and kernel size represent the number and size of convolution cores. Activation is the activation function used, and merge mode represents the combination mode of bidirectional RNN output. In order to prevent accidental experiment, all experimental results are the average value obtained from 5 experiments. 3.2. Experimental dataset. The Yahoo WebScope dataset is an open source time series data analysis dataset. The dataset consists of 4 sub-datasets, A1 to A4, with a total of 367 time series, each of which consists of 1,420 to 1,680 instances. This paper used 50 time series data in the A2 sub-dataset with strong data periodicity as the training set and 50 time series data as the test set to compare the performance of our method and other data analysis methods. Since the A2 sub-data set only contains point exceptions, in order to increase the test demand for context exceptions, this paper randomly selects an instance in each dimension of the test set as the starting position, replaces the original data in this dimension with continuous random values that fluctuate up and down no more than 30% of the value, and simulates context exceptions in practical applications, and the length of all context exceptions is between 50 and 120 instances. Use the above method to add 0 to 2 context exceptions to each dimension of the test set, and all context exceptions are independent in each dimension. The modified test set contains 99 point exceptions and 51 context exceptions. 3.3 Evaluation indicators. In order to evaluate the performance of intelligent analysis of multidimensional time series data, 3 error indicators mean absolute error, MAE, and root mean square error, RMSE, were used to evaluate the results of intelligent analysis of multidimensional time series data. Its formula is as follows, where X is the real-time series data, is the analyzed time series data, and is the length of the time series data. 3.4 Result analysis. In order to highlight the advantages of the method in this paper, the analysis method based on bidirectional LSTM, the fusion statistics method, and the bidirectional convolution LSTM analysis method are introduced for comparison, and the following results are obtained. 4. Conclusion. In this paper, deep learning is applied to the intelligent analysis of multidimensional time series data, experimental tests, so that this method can reduce the average absolute error and root mean square error of data analysis when analyzing multidimensional time series data. However, there are still many deficiencies in this research. In the future research, we hope to introduce volume coefficient to decompose and reconstruct multidimensional time series data to avoid data distortion. Thank you.